You know when you're using a tool like Git or even Google Docs, and it just instantly shows you exactly what's changed between two versions of a file? It feels kind of like magic, right? Well, behind that magic is a really powerful and honestly a pretty elegant algorithm. So today we're going to pull back that curtain and unpack the whole thing by diving into the longest common subsequence problem.
Okay, so let's dive right in. First things first, we need to get one key term totally straight. A subsequence. Now this is not the same as a substring, which has to be a continuous block of characters. Nope. A subsequence is way more flexible. You can basically pick characters from a string, and as long as you keep them in their original order, you're golden. So for A, B, C, D, E, ACE is a totally valid subsequence, but EAC isn't, because you changed the order.
And that brings us to the core problem we're going to tackle today: finding the longest common subsequence, or LCS for short. So, given two different strings, what's the absolute longest subsequence that they both share? You know, for AGGTAB and GXTAYB, the answer turns out to be GTAB. The real question, though, is how do we make a computer figure that out reliably? Let's start by looking at the most intuitive way, which, as we're about to see, is also deeply flawed.
So, a natural way to approach this is recursively. You can think of it like a detective breaking a huge case down into a bunch of smaller, simpler clues. We basically define the solution to our big problem in terms of solutions to smaller versions of the very same problem.
Here's the logic, laid out plain and simple. We look at the very last character of both strings. If they match, awesome, that's part of our LCS. We add 1 to our count, and then we just do the whole thing over again for the strings without those last characters. But if they don't match, now we have a choice to make. We have to explore two paths. What's the best we can do if we just ignore the last character of the first string? And what about if we ignore the last character of the second one? We just find the answer for both of those paths and take whichever one is bigger. And eventually, we hit our base case. If one of the strings is empty, the result is 0. Simple enough, right?
Now, this logic is perfectly sound. It will get you the right answer every single time. But, and this is a huge but, it is incredibly, painfully slow for anything other than the shortest strings you can imagine. And the reason for this, well, it's a classic trap in computer science.
You see, the algorithm has the memory of a goldfish. As it branches out, exploring all those different possibilities, it ends up calculating the answer to the exact same smaller problems, like, say, the LCS of AX and AY, again and again and again. You can picture this huge tree of calculations, and all these different branches keep leading back to the same little problems, forcing our algorithm to do the same work repeatedly. It's just a massive waste of time and energy.
So, how do we fix this colossal mess? The solution at its heart is actually pretty simple. We just need to give our algorithm a memory. And this is the fundamental idea behind a really beautiful and powerful technique called dynamic programming. Instead of recalculating everything from scratch, we're going to store our results and just look them up when we need them.
I love this analogy. Think of it like this. Our naive recursive approach is like a forgetful chef. For every single step in the recipe, he goes all the way back to page 1 and reads the whole thing over again. It's exhausting just thinking about it. Dynamic programming, on the other hand, is the prepared chef. When they chop onions, they put them in a bowl. The next time the recipe calls for chopped onions, they don't start chopping again. They just grab the bowl. They save their work so they can reuse it instantly.
And this table you're seeing, this is the prepared chef's kitchen counter. It's how we organize all our work. We create this 2D grid with one string running along the top and the other down the side. Then we just fill it in, one cell at a time, from the top left to the bottom right. Each cell's value is calculated using the values of its neighbors. And here's the best part. Once the entire table is filled out, the answer to our original, big, hairy problem is just sitting there waiting for us in the very last cell in the bottom right corner.
Now, this table-based approach, which is called tabulation, is way, way faster. We've totally solved the time problem. But, you guessed it, we've created a new problem: space. For two really long strings, like in a huge source code file, this 2D table could eat up a gigantic amount of memory. But it turns out we can be even smarter.
And this right here, this is the key insight, the aha moment. If you look really closely at how we fill in that table, you'll notice something. To figure out the value for any cell, we only ever need to look at cells in the row directly above it and the current row we're working on. We never, ever need to look 2 or 3 or 10 rows back. We don't need the whole history.
This one simple observation allows for a fantastic optimization. As you can see, this lets us go from storing that entire massive table to only needing to store 2 rows at a time. the one we just finished and the one we're building now. And with an even cleverer little trick, we can get that all the way down to storing just a single row's worth of data. It's brilliant.
All right, so enough talk. Let's see what this super optimized single array solution actually looks like in the real world. We're going to walk through the Python code that makes this whole elegant idea happen. Okay, first up, we define our function and initialize our dynamic programming array, which we're calling DP. This array's size is just the length of the second string plus 1. You can think of it as representing just one single row of that big conceptual table we saw earlier. And of course, we started off filled with all zeros.
And now we get to the main event, the loops. The outer loop goes through the first string, one character at a time. Inside, we have this absolutely crucial variable called prev. Right before that inner loop kicks off, prev gets set to 0. Its entire job is to remember the value of the top left diagonal cell from the previous state of the row, right before we're about to overwrite it. It's the secret sauce.
And this is where all the magic happens. Inside that inner loop, if the characters from our two strings match, the new value for our current spot, dpj, is simply 1 plus that pre-value we so cleverly saved. But if they don't match, we take the maximum of the value to the left, which is dpj minus 1 from the current step, and the value above, which is the current dpj from the previous outer loop. It just beautifully simulates that big 2D table using only one array.
Whew, what a journey, right? We started with a simple, common-sense idea that was just horribly slow. Then we gave it a memory, which made it super fast but kind of a memory hog, and then we optimized that space all the way down to the bare minimum. So let's put all these approaches head-to-head and see just how far we've come. This table really says it all. I mean, look at that. The naive approach has exponential time complexity. That O of 2 to the n is a total disaster for anything but the tiniest inputs. Dynamic programming gets us to a much more manageable O of m times n time. But then look at the space. The standard DP table also uses O of m times n space. Our final optimized version, it keeps that awesome O of m times runtime, but slashes the space complexity all the way down to O of n. That is a massive win.
And this isn't just some abstract coding puzzle for a job interview. This algorithm, or different flavors of it, is the absolute workhorse behind tools that developers and scientists use every single day. It's how getDiff shows you exactly what you've changed. It's the core of any file comparison tool, and it's even used in bioinformatics to compare huge DNA sequences and find important genetic similarities.
So when you get right down to it, the longest common subsequence algorithm is so much more than just code. It's a perfect example of a bigger, more powerful way of thinking. This whole idea of dynamic programming, of breaking a big problem down and remembering the solutions to the smaller pieces to build up a bigger solution, that's a mental model that applies way beyond just programming. So the next time you face a really complex task, just ask yourself, what parts of this have I already figured out?